All right, let's go and get started. A little bit shorter lesson today, but we are going to review for the quiz. I know we just reviewed in the last lesson, but then we had a weekend, and these seniors were too busy plotting a senior prank against me to get any studying done. And if I were a vengeful teacher, I would stick them with the quiz right away because it's only fair to get ahead instead of getting even. But then they would get even. So instead, I'll just be a nice teacher, and we'll review anyway so they can do well on this quiz. Some people's kids. All right. So anyway, we've been talking about an accumulation of electric charge that builds up in a body. And we call this accumulation of charge static electricity. Well, we know they weren't plotting to use any of that in their senior prank. And with this static electricity, we said that it's this accumulation of charge. And if this charge suddenly releases, then this sudden release of charge is called discharge. And we were actually playing around a few minutes ago, which is why we're getting a late start, playing around with the Van de Graaff generator again, because why not? Like, if they don't, unless they take physics in college, this is their last chance to play with a Van de Graaff generator, right? So there's my plug for taking college physics. But anyway, you're going to engineering, right? Or PCC probably. So yeah, so you'll get to play with it. You'll get to play with all kinds of cool toys. You'll go into realms that I haven't delved into, like robotics and cool stuff that if I had more time and not 4 kids and fewer classes, maybe I'd delve into. Kind of fascinating stuff that you'll get to dive into. Anyway, so you'll get to play with Van de Graaff generator later. Who knows? Who knows what the future holds for you two. Lord could always call you to be physics teachers, and then you could play with it in college and play with it every year. It's great. Anyway, we were reviewing for a quiz. Sudden release of accumulated charge was called discharge. I feel scattered today again. This is not good. Hopefully you're unscattered by the time we take the quiz. All right, however, if we allowed the accumulation of charge to slowly release into the air around us, and it would take a while, because in general we said air is an insulator, eventually the charge could just slowly leak off into the atmosphere. We call this slow, gradual release of charge. Dissipation. With charges, we said there's 2 charges, positive and negative. Negative is caused by, well, in general, what would cause Kendall to have a negative charge? More electrons. By the way, we did determine our Van de Graaff generator, the way the rollers are placed, actually accumulates a negative charge, is what we concluded. We get a negative charge on our Van de Graaff generator. So anyway, we were, like I said, playing around with it. So extra electrons, right, is a negative charge. Positive charge then would be caused by a deficiency, a lack of electrons. And of course, if everything's in balance, we would simply say that the object is neutral. And with these charges, we said the law of electric charges, let's say it together as a class, like charges repel, opposite charges attract. And Michael said it right there with us. Good job, Michael. And now, Michael mentioned an anion a moment ago. What is an anion?
A negative ion.
A negatively charged ion, and a cation would be a positively charged ion. And it's the ions that carry charge in a gas or in a liquid. Now, in air, you may also have a few free electrons that could be carrying the charge also. But largely it's ions that carry the charge in gases, and strictly the ions that carry the charge in the liquid. In a gas, then, air, like I said, generally an insulator. But if you get a big enough charge difference, as we got to see really well today, thanks to a grounding wire, which made all things possible. Shout out to Miss Morse for the use of her grounding wire. Anyway, if Miss Morse is proctoring this class next year, ask me about it after class. Anyway, our grounding wire allowed us to get a really good
charge,
a spark. The release of electric charge through an air takes a pretty big, significant charge difference, and get that nice bright discharge as a spark. What about in solids? Ions do not carry charge in solids. What do? Freelance electrons, we call them. Delocalized electrons. Anyway, delocalized electrons are abundant in materials known as,
So, metals.
well, metals are a good example. Conductors, good. Conductors, delocalized electrons are abundant in conductors. They are absent in
Wood.
insulators and scarce in semiconductors. Your four major conductors, best conductors.
Silver, copper, gold, aluminum.
Good. And then your two prominent semiconductors,
Silicon, germanium.
silicon and germanium. We talked about transferring a charge. So we could transfer a charge by,
Contact.
which is contact, which is called
Conduction.
conduction, which results in
Equal acts. Equal charges.
equal strength. Well,
Equal strength.
they're equal strength with each other after the charge transfer has taken place, but
Weak.
it's weaker than it used to be because it's shared. And it's also not just equal strength, it's actually the same type of charge, whether positive or negative. Where the other type of charge transfer, induction, produces the opposite charge through induction. Also, the charge will be equal to the original charge strength because nothing is shared, because the two objects come in close proximity, but they do not touch. For the charge to actually transfer, it requires the use of a ground wire, and the ground wire must be cut or removed in some way. We tried that. Cut or removed in some way for the charge to last. We talked about a device used to test the charge of an object.
Electroscope.
Electroscope. And we said the key for the electroscope is you have to give it
A charge.
a known charge right up front, and then watch how the
Foil leaf.
foil leaves respond as you place it in your objects. If the foil leaves don't respond, then that just means the object you're testing
Neutral.
is neutral. If the leaves spread out further,
Same charge.
it's got the same charge you gave the electroscope, and if they come together,
Opposite.
opposite charge. Again, that's when you do what with the electroscope?
Bring it near.
Bring it near. Don't touch, but bring it near. You're using induction to test. We talked about a French scientist, Charles de Coulomb, who came up with the law of electric force. Not electric charges, that's like charge repel, opposite charge attract, but the law of electric force. And in fact, the Coulomb is our SI unit for charge, right? Not force. Force is Newton, but Coulomb talked about force and said force depends on a couple of things. First of all, the force of attraction or repulsion depends on,
Okay.
well, K is a constant proportion. It doesn't really depend on K. K is just kind of there. It depends on
Absolute value of the charge.
the strength of the charges. Stronger charges will attract or repel more strongly. That makes sense. It'll also depend inversely on
Distance.
the distance between the charges. So what was our equation for F?
K times the absolute value of Q1, absolute value of Q2 over R squared.
There we go. And so that was the law of electric force. A lot of scientific notation in there. What was that value for K? Newtons times meter squared per Coulomb squared. We talked about as an electric body, electrically charged body exists. As you get near the body, you begin to feel the effects of its,
Electric sphere.
not electric sphere, but electric field. It's electric field that it gives off. And if we wanted to see how strong the electric field was at any point, we could take a little test charge, I don't know, maybe a charged balloon, and put it near the charged body and just see how strong is this charge. The force of attraction or repulsion for that particular object at that particular location determines the electric field strength at that particular location. Gives us our second equation in this chapter.
E equals F over Q sub naught.
There we go, where electric field strength is measured in
Coulomb. No, force newtons. Newton force. Newton.
newtons per coulomb. We have newtons over coulombs, so newtons per coulomb. But we said that a better way to think of electric field is, of course, since the strength of the charge determines the attraction or repulsion, the field will be stronger with a strong charge. Also, the further away you get, the weaker the charge is, so therefore the weaker the field is. So if we wanted to show the strength of an electric field at a given distance from the charged body, We tied the two equations together to come up with our third equation.
E equals K absolute value of Q over R. Squared.
There we go. We just tied the two equations together. We said that force, we use an absolute value to take care of the signs, get rid of them, because we're going to put our own SIGN on our force. If the force is attractive, positive, and if the force is repulsive,
Negative.
negative. We also talked about how if you were to, and we won't, put little grass seeds in a little oil bath and run an electric current through, you could see where the lines of electric force form, these lines of force. I said there's a few things we need to remember about the lines of force. One of them is that lines of electric force always begin in a
Circle.
no. Lines of electric force are drawn, from a positive body outward. Okay, so if you have a positive body, they're outward. If you have a negative body, then they go inward. So if we have a negative body, then the lines of electric force would run this way, from the positive into the negative. If you had a couple of negatively charged bodies, again, the lines of force are trying to draw in both directions, which means they more or less repel each other, because they're going inward in both directions. So we kind of see how that repulsion takes place somewhat. And of course, attraction between the positive and the negative. Lines of force have to be drawn how to the surface?
Perpendicular.
Perpendicular to the surface. Now, if they're rounded, that would be in line with the radius, but perpendicular to the surface. And if you have stronger charges, you draw more lines closer together. All right, everything else we worked on already. Questions on this? All right, in just a moment, we're going to take a quiz. Let's get our homework assignment for this evening copied down because there is no actual lesson today. Just given some things that I need to get done this hour with academic fair coming up. So your homework for this evening, and you'll work on this when you finish your quiz, is to read pages 379 to 384. Read pages 379 to 384. Read pages 379 to 384. On pages 397 to 398. Pages 397 to 398. Answer questions 1, 2, 4, and 5. Page 397 to 398, answer questions 1, 2, 4, and 5. We're going to be talking about current in our next lesson. Skipping over some interesting chapters. We just don't have time to cover them because my days with you are getting shorter and shorter, fewer and fewer, I guess I should say. So, if you want to read over chapters 23 and 24, magnetism, electrical generators, alternating direct current, interesting stuff, but I want to get to circuits because I want to finish out the year with that. Something, again, that I had struggled with in high school, and I think I can help you understand them better than maybe I did. All right, so that'll be your homework. We'll look at that in our next lesson. For now, clear desk except for a clean sheet of paper and a pencil and a calculator. Clean sheet of paper, pencil, calculator, everything else away. First and last name at the top of your paper, along with today's date, which is 4/24/23. 4/24/23. And this is quiz 26. Quiz 26. Let's take a look at the quiz together very quickly. First and last name, 4/24/23, and quiz 26. Numbers 1 through 9, completion. Write the word or words that need to be used for those. 10 through 14, short answer. Number 10, briefly describe, but mini essay there. Don't go into too much detail, but I do need for number 10 you to answer the question fully. Okay. Number 11, write that out. 12, write the equation. Number 13, there's 2 equations for you to write. And then number 14, just kind of finish the 2 blanks, so to speak, that are more or less left there with the ... 15, 16, 17, you got some problems, write equations and solve. I do want to point out on number 17 that the positive charge is being repelled. The positive charge is being repelled. I want to make sure I pointed that out on number 17. All right. You may begin.